We're going to be talking about instantaneous rate of change, otherwise known as I.R.O.C. So we have the instantaneous rate of change. And what it is, it's another name for a derivative or a slope of a tangent line. And it's usually used to find the exact rate of change in velocity, population, temperature at a certain time t. So again, I.R.O.C is instantaneous rate of change, and you're finding the exact rate of change in something, whether it's a velocity at a specified time t. So here's an example illustrating instantaneous rate of change. So we have an object that's 3,000 feet above the ground, and we're given this equation. The height off the ground is 3,000 minus 18t squared, and we want to find the object's instantaneous velocity at t equals 3 seconds. So at 3 seconds, what's its velocity? So if you recall, the formula to find the derivative is this. So using limits, we'll be finding the limit as h approaches 0 of f of a plus h minus f of a all over h. Well, a in this case happens to be the time. So we're going to find it at 3 seconds. So I'm going to replace this a with a 3. So what I'm going to go ahead and do first is I'm going to evaluate the function at 3 plus h. So everywhere there's a t, I'm going to plug in the 3 plus h, since t is the variable in the equation, not an x. So I'm going to get 3,000 minus, and then I'm going to get 18 times 3 plus h, and then I'm going to have that squared. And then I'm going to have minus, and then when I plug in 3, so we're going to take this 3 and then plug it in. I'm going to subtract off the whole thing. So minus 3,000 minus 18 times 3 squared. And so I am going to now simplify that, and that's all over h. Alright, so now what I'm going to go ahead and do is I'm going to go ahead and simplify the numerator. So I'm going to end up getting the 3,000 minus the 18, and then I'm going to FOIL this out right here. So I'm going to get a 9 plus a 6h plus an h squared, and then this right here, a 3,000 minus an 18 times that's a 3 squared, ends up being negative, or ends up being 2838. So I'm going to have minus the 2838. And this is all over h. So now I'm going to go ahead and distribute this negative 18 through. So I'm going to get 3,000 minus, and then I end up having minus 162 minus 108h minus 18h squared, and then minus the 2838 all over h. Alright, so now let's simplify. When I end up combining the 3,000 minus the 162, I end up getting the 2838. Notice how these end up canceling. Your numbers should always cancel. You should only be left with things with h's when you're finding derivatives. So now I can cancel this h with that one, and then this one will also cancel with one of those. So what I'm left with is negative 108 minus 18h. Now I can find the limit as h approaches 0. I can now plug in 0. So I'm going to get 18 times 0, and so basically I get a negative 108. So if you look at the original problem, we wanted to find its instantaneous velocity after 3 seconds. And so what we have is this object is falling exactly at 3 seconds after it's dropped. It's going negative 108 feet per second since it's a velocity. So that's I.R.O.C, instantaneous rate of change. You'll basically find the derivative at whatever the time is at that specified point, and the derivative is the exact velocity at that point. So moving on to the next thing, we're going to be finding limits at infinity and negative infinity, and the process that you're going to be using is this. So you're going to be locating the dominant term, and so usually it's the term with the highest exponent. So once you have that, or once you've located it, you're going to have one of 3 cases. Here's the first case. So if the dominant term is in the denominator, so it's in the bottom of your fraction, the limit as x approaches infinity or negative infinity will always be 0. So the second case is if the dominant term is in the numerator. Then if that's the case, the limit will be either infinity or negative infinity. And what you're going to have to do is you're going to have to plug in large x values to see which one it is. So the last case is if the numerator and denominator have the same dominant term. And when this happens, the limit will be the ratio of the coefficients of the dominant terms. So what you'll be doing is you'll just basically be taking the numbers out in front of the dominant terms and dividing them. So in this case, the limit is going to be a horizontal asymptote on the graph of f of x. So I'm going to show you all of these cases in just a minute. So just remember that if you have, for this last case, the dominant term is in both the numerator and denominator, then you're going to be taking the ratio. Ratio means you're going to divide the coefficients of that, and that just is going to be represented by a horizontal asymptote on the graph. So here's some examples. So our first example, we're going to be finding the limit as x approaches infinity. Notice you're going to only use these at limits at infinity or negative infinity. And you're going to first find this process right here. You're going to locate the dominant term. It's the one with the highest exponent. So it looks like the dominant term is in both the numerator and denominator. So that's case 3 right over here. So what you're going to be doing to find the limit is taking the ratio of the coefficients of the dominant terms. So you're basically going to be dividing the 3 over the 6, and this is going to be your limit for the graph. So the limit will be 1/2. Let me show you with the graph. So if you look at what we're approaching, as x gets bigger and bigger, here's positive infinity way over here. Our graph is approaching this asymptote. Remember I said in this case you're going to have a horizontal asymptote if you're taking the ratio of the coefficients? Well, if this is 1 right here on the graph, this asymptote is at 1/2. So this graph, or the y values, are approaching 1/2 as x approaches infinity. Okay, so in this next example, our dominant term is in the denominator. We have an x to the 5th in the denominator. So this is going to be the first case right here. It says if the dominant term is in the denominator, the limit will always be 0. So I can automatically say that if I were to look at the graph, it'd be 0. So let's check it out. So I went ahead and typed in the equation, and remember here's positive infinity over here. So as I trace the graph, as x gets bigger and bigger and bigger, our graph is approaching the 0. So there we have the limit, or the y values are approaching 0 as x gets larger and approaches infinity. Alright, so for this next example, we have as x approaches infinity, we want to find the limit, and we're going to first locate the dominant term. The dominant term is in the numerator. So this is going to be the second case. If the dominant term is in the numerator, then the limit's going to either be infinity or negative infinity. And you can do one of two things. You can either look at the graph, so you can type this whole thing into your graphing calculator, or plug in really large x values to see which one it is. So let's look at the graph. So here's the graph, and here's positive infinity along the x-axis right there. So as I trace the graph, so the graph looks like this, as x gets bigger and bigger and bigger, our graph is going to get larger and larger as well. So it looks like that the limit would be infinity, just looking at that graph. And the way you could do this without a calculator is you could just start plugging in like 100 to the 4th times 3 plus 2, then like 1,000 to the 4th times 3 plus 2, and as the larger the x gets, so does the output, or the y's. So that's how you do it, just by plugging in x's. So in this next example, locating the dominant term is a little bit more difficult for some. When you have an exponential, the one with the larger base is the dominant term. You may not multiply those two. That is not equal to 6 to the x. Remember, order of operations, multiplication does not come before exponents. So this is not 6 to the x. So the largest term would be this. That would be the more dominant one. So what we're going to do then is we're going to plug in large values of x. So remember, x is getting bigger and bigger and bigger. So if I were to plug in like 10, then 50, then 100, and make x get bigger, and plug them right into this exponent right here, I'm going to have a negative 5 to the 10th, then a negative 5 to the 50th, and then negative 5 to the 100th. What happens is those values end up getting more negative or smaller, so we're going to go to negative infinity, just because of this negative sign out in front. This is always going to be a negative answer, and then you're just going to multiply that by powers of 5. Looking at the graph, here's what you could get as well. So when I look at the graph, as x approaches infinity, so as x gets bigger and bigger and bigger, here's positive infinity, our graph is going negative. So that's how you have negative infinity. So a graph will tell you everything. If you go ahead and put it in your graphing calculator and graph it, you can find any limit at infinity or negative infinity just by seeing where the graph's going. So this next example, it looks like our dominant term is this right here, this 9x to the 7th. But notice what x is doing. It's becoming more negative. It's approaching negative infinity. So if I were to plug in x values into here, let's just say negative 100 and then negative 1,000, and x gets smaller and smaller and smaller, what's going to happen to this term right here? Well, if you remember, if it's an odd exponent and you have a negative number to an odd exponent, it's going to always be negative. So what would happen is a negative number times this 9 is going to still be negative. So all these values are going to get smaller and smaller and smaller, or go to negative infinity. You can also look at the graph. So here's negative infinity, because remember we're approaching negatives this time. So as I go to the negative infinity, my graph is going negative, so I can see that my y values are becoming smaller and smaller and smaller. And again, what I did is I just plugged in x values, starting at negative 100, then went to negative 1,000, made my x values get smaller, and then when I raised it to the 7th, it was still negative. Multiplying by 9 just made it go more negative, so overall, my y values are negative infinity. So here we have the limit as x approaches negative infinity of this expression, and I have a dominant term in the denominator. It's this case right here. Whenever the dominant term is in the denominator, because that's the only place there's a variable, the limit's always going to be 0. So this whole piece right in here, this goes to 0. So what I'm left with is just the limit as x approaches negative infinity of 3. Well, that means that the y value is always just going to be 3. And here's what the graph looks like. So if I were to look at negative infinity, so as x approaches negative infinity right here, it looks like our graph as I approach negative infinity is approaching y equals 3. And so there we have it. In this next example, I wanted to kind of illustrate a common mistake that I do see a lot. People automatically tend to think, oh, here's the dominant term because it's squared, and they forget that these two are multiplied down there. Well, if I were to go ahead and multiply that out, the denominator would actually come out to be a 2x squared, and then I'd have a minus 6x and a positive 1x, or a minus 5x and then a minus 3. When you look at the dominant terms, you have them equal, one in the numerator and one in the denominator. So what you would have to do then is do case 3 right here. If it's in the numerator and denominator, you're going to be taking the ratio of the coefficients. So the coefficients would be the 5 and the 2. So the limit would be 5 halves, or 2.5. To illustrate that with a graph, we're approaching x equals negative infinity, so here's the negative x values. Our graph right here looks like it's crossing or approaching, if I were to draw kind of a line right here, here's 5, it looks like we're about right. It does look like it's approaching this graph at 2.5. Okay, so my last example is the limit as cosine approaches, or as x approaches negative infinity of cosine. So if you remember what the graph of cosine looks like, it's here, and if I want to find what happens to the y values as x approaches negative infinity on this side, what's happening is I approach negative infinity, I'm oscillating, I'm going up and down, I'm not approaching a single number. So when this is the case, if you remember when we were calculating earlier, when it oscillates in the table, whoops, I didn't mean to write that, that means that there would be no limit. So you would have does not exist. So if it's not approaching a single number and it's kind of all over the place, the limit does not exist. Alright, that's it. I will see you guys tomorrow. Have a great evening.